Hi, my name is Joshua Simmons, and today I'll be presenting about some work that I did with Dr. Kristen Splinter while I was at the Water Research Laboratory for UNSW Sydney. This work was looking at combining both data-driven approaches and numerical modeling approaches to predicting storm erosion. Now, this is a particularly important topic because of the growing prevalence of early warning systems around the world. In particular, here we're talking about sandy beach erosion, and when we're applying models to forecast sandy beach erosion, we really need to be sure that we've assessed the accuracy and limitations of each of these existing modeling approaches before we apply them. In addition, I think it's important to explore the role of historical storm data and how this can improve our forecasts in these types of systems. And that leads into our key questions for this particular presentation, and that's: can a long-term data set be used to effectively train a machine learning algorithm to predict storm erosion? And how can model averaging be used to overcome individual model limitations and provide the best performance for storm erosion prediction? Our data set for this study comes from Narrabeen Collaroy Beach in Australia, where we had around 40 years of data. Now, this is profiled data measured at 5 different locations along the beach, and this was measured at about a monthly frequency. To go with this data, we had the wave conditions associated with the periods between each survey, and that came from the Corker wave hindcast. From this data set, we created a storm data set. So what we were looking at were different storm events and the changes in beach morphology that they caused. So we define a storm in this region of the world as the significant wave height exceeding the 95% threshold for 6 hours or more, or the 75% threshold for 72 hours or more. So in Sydney, that 95% threshold is about 3 meters significant wave height. From our data set of monthly observations, we can find the change in beach width and the change in volume that are associated with those different storm events. And overall, we extracted 343 different data points where we had a pre-storm and a post-storm morphology and some sort of storm event happening in between, one or more. We trialed 4 different models to produce predictions of storm erosion. So these were 2 numerical modeling approaches, that was S-beach and X-beach, and also 2 data-driven approaches, so an empirical model and also a machine learning model. The first model I'll talk about is an empirical model, and that was developed by Harley and Turner in 2009, and essentially said that the change in beach width or the change in volume was related to purely the cumulative offshore wave energy from each individual storm. So there were 4 parameters to fit in this model, and they were fit using a different data set from Argus imagery using 89 storm events. There were 2 cross-shore erosion models used, and those were S-beach and X-beach, and they purely model the transfer in a cross-shore sense only of sand from the subaerial beach to the bar in a storm or multiple storm events. So the first of these was S-beach, which is a semi-empirical model, and this was calibrated previously at this site. And the second of these was X-beach, which is a more process-based model with much more physics and a lot more complicated model. And again, this was calibrated by a colleague at Narrabeen Collaroy. Finally, we had a machine learning model. So as far as neural networks go, it wasn't too complicated. 2 hidden layers of the sizes you can see there. And in terms of input variables, a number of different combinations of different hydrodynamic variables were trialed, from 2 to 8 input variables. And the final model had 4 variables. These were beach storm width, so the response of the beach is really dependent on the antecedent conditions. The cumulative wave power breaking, so this was the nearshore energy available to actually move sand around. The maximum offshore significant wave height, so an indication of how big that given storm event was. And also the mean 2% exceedance wave run-up from using the Stockton equation, and this included the water level as well. 343 data points were divided into training and test sets, and then a cross-validation process was undertaken to determine the model performance of each of the individual models. As you can see in the top panel, the machine learning model performed best overall on all the data. When we look at the bottom panel, we find the performance of the different models on the largest 10% of storms in the test dataset. We can see that this changes the performance of the models. The machine learning model does not perform as well as the empirical model for these large storm events, which are of most interest when we're considering an early warning system. When we look at the distribution of errors across all the different storms, we can see that the XBeach model in red tends to overpredict the amount of erosion, so a positive error across the entire data set. So we can see this both in the shoreline prediction and also in the volume prediction. The empirical model similarly does tend to overpredict the amount of erosion that was observed, and we also see for both of these models that there's a large variance in the error, so they are quite noisy in their predictions. The machine learning model and the SBeach model have much less variance, and the machine learning model in orange here tends to fit the data best overall. When we look at the largest 10% of storms in the bottom panel, we can see that the machine learning model in orange here does tend to underpredict the amount of erosion that was observed. And similarly for the SBeach model in green as well. The XBeach model still does tend to overpredict a little bit, but the predictions are much better, and the empirical model is just about centered on an error of 0, but still with a really large variance. This indicates that the XBeach and empirical models could be potentially better fit to these more extreme events. And we don't have time to discuss it fully here, but these different models will definitely be influenced by the type of data that's used to both formulate them and to calibrate them. We can now look at methods of how to combine the 4 individual model predictions to provide a better overall prediction. So we can look at these weighted average models. So it's a weighted average of each of the 4 individual models to produce a hopefully better performing model. Now we can see that we use here the method of Bates and Granger, which is quite an old method, and it essentially says that the weight of each model should be proportional to the model's prediction error variance. So if we have a look at our distribution of errors over here, we can see that the machine learning model is given quite a high weighting because it has quite a low variance in its errors, whereas the XBeach model is given quite a low weighting because of the large variance in its errors. When we look at the combined model performance, it performs about as well as the machine learning model for the overall data. However, on the largest 10% of events, which are the events of most importance within our data set, it performs better than any other individual model and significantly outperforms the machine learning model. As part of this study, we trialed several different model averaging methods. Some of these were pretty basic, so an equal weighting of the 4 models, and others required some sort of fit to the training data. And obviously the results presented here are for the test data. So we did some ordinary least squares fitting both with and without a bias as well. What you can see is that there was always a trade-off between the model performance. So some of the models might have performed better for the overall data, but not as well for the largest 10% of storms. And that was where we chose that Bates and Granger approach as a good trade-off. What's clear is that our model weightings should be adaptive based on the characteristics of the storm events. So we can see that in a really simplistic scenario here, we've fitted the model weights to the observed change in volume from the training data set. And so this is not useful in a forecasting sense because we would not know that information a priori, but it's useful in a descriptive sense of what our 4 individual models are doing for this data set. So we can see for the smaller events that we would like to weight the SBeach model and the machine learning model more highly. So these are the models that did best overall in the dataset. The empirical and X-speech models in red and blue down here, we tend to weight them more lower for these smaller events because we don't want those false positive over prediction of these really moderate events to influence our forecast. As the events get more extreme, we would like to trust the X-speech model more and give higher weighting to this model compared to the other three. We tried a number of different methods to fit our model weighting values dependent on the characteristics of the storm. However, our data proved to be too noisy from this dataset to implement such an approach. I think this is a combination of the errors of our models, which were quite large at times, and also the surveying frequency of our data set, which was monthly for the most part, which could include several storm events and could include some recovery during that intervening month. To summarize, the machine learning models provided the best performance over the entire data set. However, these were not the most accurate model for predicting large storm events. This could be due to the training set that was available to these machine learning models and the absence of a significant number of those really extreme events within that data set. With extra data, this could be improved and the model could be more balanced between more moderate events and more extreme events. The X-speech and empirical models had a tendency to provide false positive predictions during small events, tending to over-predict what was actually going to occur for those more moderate events. Predictions of storm erosion were found to be significantly improved through model averaging, and with more data, both the machine learning techniques mentioned previously and also model averaging techniques can be improved significantly. In particular, we can choose model averaging weights that correspond to the characteristics of the storms that we actually want to model. So it's really important that we continue to think about our data sets that we're collecting and how we can perhaps collect data immediately prior to and immediately post storm events so that we can get the most accurate data for these sorts of early warning and forecasting system applications. Thank you very much.